All right, so in class we talked about what happens in this portion right here where the spring is still compressed, but we didn't talk about what happens when the block releases from the spring. And at that point, you have no spring energy. All you have is the kinetic energy of the block. But as it slides, it's slowing down. So it's losing kinetic energy due to an external force. And that would be the force of friction, which acts opposite the direction of motion, is sapping energy from the block. So let's go ahead and start by drawing a free body diagram for this red highlighted portion with friction. So we're going to have mg as always, our gravitational force, and our only other force in the y direction will be Fn. That's the ground pushing back up, the normal force, and opposing the direction of motion will be Ff. Now, Fn is equal in magnitude to Fg because the block is not accelerating vertically. The formula for friction force is mu, coefficient of friction, times Fn. And because we know Fn is mg, we can replace Fn with mg. And we can actually solve for the force of friction because we know mu is given as 0.08, and that's unitless. The mass is 0.5 kilograms, and the value for g we'll use 10 newtons per kilogram. So we get a friction force of 0.4 newtons. All right. Now, friction is doing work, negative work, on the block as it slides, right? Because the block is traveling in this direction and friction is friction is acting in the opposite direction. So our formula for work is F parallel D, right? And F is parallel to D. If you were using FD cosine theta, in this case, theta would be 180 degrees, and then cosine of 180 would give you -1. So that helps reinforce the fact that the work is negative. So just want to show you, if you replace F, the friction force, right? So I should more clearly show that the force that's doing the work is friction, and the value of that force is 0.4 newtons. Now, notice we have an equation here that says the amount of work done is based on the distance, right? The longer the block slides, in other words, the longer it is displaced to the right along that rough surface, the more work is done. And eventually enough work is done so that the block comes to a stop and all the energy is sapped. So we can use this equation right here to calculate the amount of work done. So for this position, this first position in the table, after the natural length of the spring, we've got x is 0.5. We can simply calculate the frictional force, 0.4 newtons, times the displacement, 0.5 meters, and we get an amount of work done as 0.2 newton meters, or 0.2 joules. So that's how much work is done in 0.5 meters. So in the table right here, right, our position is 0.5. Our spring energy is 0 because we've released the block. Our kinetic energy we can solve for in a second. So the work done up to this point, we just calculated it as 0.2 joules. Well, we know our system before we started losing energy, right? Up to this point, the amount of mechanical energy in our system was 1.0 joules. Well, we just lost 0.2 joules because of friction, so we're down to 0.8 joules in our system, right? And if we wanted to show that with a calculation, we'd have to choose like an initial and final position. And I would probably choose, the release point right here as my initial position, and I would choose 0.5 as my final position. And then I could say, mechanical energy initial plus work is equal to mechanical energy final. And we know that we had 1 joule of energy. Sorry, that's a little hard to see. We had 1 joule of energy in our system at the position of 0. The amount of work done was negative 0.2 joules. So our final mechanical energy, right, would calculate to 0.8 joules, will be ME final. So this is the important part here, is that the negative work is being done on our system. And if you're wondering where the 1.0 came from, that came from calculations we did in class. For all of the rows right here, all of these had a mechanical energy of 1.0 joules. And that would be true all the way up to a position of x equals 0. And now we start losing 0.2 joules, right? You travel another 0.5 meters and you would lose another 0.2 joules. Let's show the calculation for that. So work equals FF times D, 0.4 newtons of friction. This time for D, I would use 1.0 meters, and I would get a work of 0.4 joules. So at this point, we've lost 0.4 joules, and when I say lost, I mean from the point where it's frictionless, where we hadn't lost any energy, and now we're down to 0.6 joules of energy. And because you know there's only kinetic energy in the system, right, the mechanical energy has to be equal to the kinetic because we have no spring energy. So the rest of the table would look like this, 0.4 joules. This would be 0.6 joules. You can just kind of see the pattern in the numbers, right, from 0.2 to 0.4, 0.6. It's linear. It's the amount of work done is linear based on the formula W equals FD. So if we keep on going, we'll see that we're almost out of energy, and the sheet, I think, stops there. If we were to add one more row, right, by then the block would be stopped because the amount of work done in 2.5 meters is equal to exactly 1 joule, which is how much energy we started with. So again, this is FF times D, and for 2.5 meters, if you multiply that out, you get 1.0 newton meters or joules. So at that point, all of the energy has been removed from the system. So because it's decreasing linearly, if we were to complete this graph over here, on this side, if this was 0 and every 4 squares is 1, if this is 2 and this is 3 meters, you'd be out of energy at 2.5 meters. So in class, we had about 5 blocks to indicate 1.0 joules of energy, and it would decrease linearly because every time you travel, the block travels 0.5 meters, it loses how much energy? 0.2 joules. So yeah, so there's a pattern. Every time you travel, we calculated, every time you go 0.5 meters, you lose 0.2 joules of energy, and that pattern continues all the way down until you get to 2.5 meters.